Now we're going to look at the first two skills of functions, determining whether a relation is a function, and then understanding function notation. But before we talk about those two things, let's give the basic definitions of functions versus relations. The first thing is a relation, and a relation is how quantities are related to one another. No specific rules, nothing one-to-one, just how does something relate to one another? 7 goes with 9, 12 goes with 3, 7 goes with 3. Just a relationship between two pieces of information. The second, more condensed version of a relation, or a more specific version of a relation, would be a function. And a function is where an item in one set matches exactly one item in another set. And the way you looked at functions previously in math is you said that there is one y value for any given x value. One y value for any given x value. And visually or graphically, the way you looked at that was you did the vertical line test. So if I had a graph that was a sideways parabola and I drew a vertical line, if that vertical line crossed the graph at multiple points, the graph was not a function. This was not a function. This is called a relation. But if I have a graph such as this, where I draw a vertical line through at any point along the graph, and the vertical line only crosses that graph at one point, then this is a function. It's also a relation, as a function is a special type of relation. The other way you described a function was that a value in the domain, or the x values, can only produce one value in the range, or a single y value. So domain are x values, range is y values. A value of the domain can only produce one value in the range. So the first thing we want to look at is, do these sets of data represent a function, or are they just relations? So the first one, 2, -2, 3, 0, 4, 1, 5, -1, does each one represent this, or combine a function? And this one, the answer is yes. The reason for that is each x value only goes to one y value. Here 2 goes to -2, 3 goes to 0, 4 goes to 1, and 5 goes to -1. If I had a relation instead of a function, I might have something like 2, -2, 3, 0, 4, -2, 5, -1, and then 2, 7. So I changed a couple of numbers right there. The reason this one would not be a function is this part right here. The fact that my two 2's go to a -2 and a -7. So my x goes to two different y values. So that would be something that's a relation and not a function. The second example here, 3, -2, 5, 0, and 2, -3. Yes, that one is a function as well. Once again, all my x's go to only one value in the range, or one value for the y's. The second concept is function notation. And when we got function notation, we talk about f of something, f of a variable. And specifically, we talk about f of x. The symbol f of x is function notation for the value of f at x, or simply f of x. In function notation, the x is the independent variable, meaning that we can choose what we want x to be, and the f of x is the dependent variable. The independent variable is just a placeholder in the function. Previously, we saw that f of x is equal to y, and that's perfectly fine to think of in your head, but we want to get to the point now where we're not replacing f of x with a y. we want to keep f of x as a function, as we'll be dealing with a lot of function notation this year. So here's an example. F of w is equal to w cubed plus 3w squared minus 9. Describe how to find f of negative 3 and then solve f of negative 3. So here's a describe. This would be a verbal explanation of what we do, and then we'll do the analytical or the algebraic. So the describing piece is wherever you have a w, you will replace it with a negative 3. So my w's are going to become negative 3's. And then to find it, we'll use our rules of algebra in order to simplify. So here, f of w is going to become f of negative 3 is equal to negative 3 cubed plus 3 times negative 3 squared minus 9. And we'll simplify that down. Negative 27 plus 27 minus 9 is equal to negative 9. So f of negative 3 is equal to negative 9. Do not fall into the pattern of saying I've got to divide through by negative 3 to get that f by itself. This is function notation, so my final answer should be in function notation. So f of negative 3 is equal to that negative 9. The last example for this skill then is example number 3. If g of b is equal to b squared minus b minus 6, solve g of x plus 5. So in the same idea here, wherever we have a b, we are going to now replace it with an x plus 5. So here I want g of x plus 5 is equal to x plus 5 squared minus x plus 5 minus 6. Being very careful to make sure I put parentheses around the entire quantity that I'm substituting in. And then we'll simplify on the right-hand side. X plus 5 squared, if we FOIL that out, is x squared plus 10x plus 25. We'll distribute our negative in. And then we'll combine our like terms. So x squared plus 9x plus 14. So g of x plus 5 is equal to x squared plus 9x plus 14. So what that's saying is if I plug x plus 5 into my function as my input, my output then is x squared plus 9x plus 14.